Okay, we are a couple of minutes past the starting time, so we think we can get started here again. So welcome everybody again to the seminar series on diffusion chronometry. And we've been running this for a couple of months now, once a month, fourth Thursday of every month. And thank you for all your feedback and all your interest and joining in. So it's been very pleasant to have all of you join in and discuss and interact. And we hope that we continue that on today with a set of 2 more talks with 3 speakers, as it turns out. So we'll get to that. But the first talk today is by Chiara Petrone. Chiara is at the Natural History Museum in London, UK, but she's been in all kinds of places before she ended up here. So I was just looking through her CV quickly, and she's been in Kyoto in Japan. She studied in Florence, where she got her PhD as well. But then she's been in Kyoto in Japan, in the Carnegie Institute in Washington, in Cambridge, and has been in London for a long time. So she works on alkaline and subalkaline magmas and volcanism and different aspects of it. And in particular, she works in different areas of Mexico and different Mexican volcanoes. She's going to talk today about reconstructing magma dynamics via elemental diffusion chronostratigraphy. And I'll let her get started, and then I'll introduce the other speakers at the end of her talk. That will be Christy Till and Adam Kent, so we'll get to that later. But for now, Chiara, it's all yours.
Thank you very much, Shumi. So I'm sharing my screen. Okay, I hope you can see that, and you can see my pointer as well, hopefully. Yeah. Okay, thank you very much. Thank you for the invitation. And yes, so I'm going to talk about some recent work on the non-isothermal diffusion work that I've been doing and trying to reconstruct the diffusion profile, core rim diffusion profile in complex crystal as much as possible, what I call a chronostratigraphy. And I will show some example how this can help to better understanding the magma dynamics. Okay, so if I can. Okay, it's working, sorry. Okay, the first thing that we really need to ask is about which processes are we targeting. So here is a recent compilation from Fidel Costa from last year, looking at the mixing to eruption timescale for different volcanoes from basalt to rhyolite. Many studies generally that look at the mixing to eruption timescale, they generally focus on the last stage of the rim growth. And this is for very good reason, because the last stage captured the time scale relevant to the most recent magma mixing event. So it is assumed that this stage of mixing and crystallization take place in the shallow magma reservoir. And so what we model is the duration of the relevant to the final location of magma, the assembly and residence prior to eruption. However, when we look at the sorry, I don't know why my screen is not going very, very quickly. But in any case, when we look at the population of crystal in any rock, what we can see is that they really record a very complex history, most of the time a non-isothermal one. So what we can see here from this sketch from a paper from Ruth et al. Last year is a crystal that is growing, and each layer forms a different temperature. So and we know that the diffusive chronometry starts upon the formation of the chemical gradient. And the diffusion doesn't stop even when the gradient or the boundary, the chemical boundary is isolated from the melt by the overgrowth of a further external crystal portion. The only thing that change is that the diffusion, the temperature, the diffusion occur. So really, since the magmatic processes are non-isothermal, probably if we just model the diffusion at the temperature of the rim, probably this is not quite correct. And this has been known for quite a long time. So we can see here from the last decade, this is a work from Mar and Cal, which I think is the first that's really recognized the need to consider the difference in temperature. This is a work from on Etna volcano, looking at the olivine zoning pattern. By a system analysis of the olivine zoning pattern, Maren was able to reconstruct different magmatic environments, each one characterized by different chemistry and temperature, and how the olivine moved from one magmatic environment to the other via this very complex system. After that, so another example is this one from Druid et al. From Santorini volcano, where they here there are some plagioclase that have an inner core grown in a dacitic melt at 900 degrees, and then they are surrounded by core and rim from a rheodacitic melt at lower temperature. And what they show in this paper very nicely is the difference between using one-step model with the single temperature of the rim here, where the the red curve doesn't really match the observed profile. And when instead they consider the two-step model using the two different temperatures, one for the core and the other one for the rim. And actually then there is a very good match. So starting from this paper and from this approach, a few years back with my some collaborator, we proposed what we call the NIDIS, a non-isothermal diffusion incremental step model. In this model, this is a multi-step approach that allows resolving the time scale in complex zoned crystal. So trying to resolve more than one boundary and trying to resolve the crystal as much as possible. In this left-hand panel, we have the forward approach. So simply the crystal, in this case, a pyroxene is growing from a low magnesium, low temperature core. Then there is a high magnesium, high temperature overgrowth, and the diffusion starts to kick in at the temperature of the high magnesium melt. At some point, there is a rim forming at low magnesium, with a low magnesium composition and low temperature, and the diffusion continues for both the internal and the external boundary, but at the temperature of the rim. So we used the backward approach, starting from the rim. We deconstructed the core rim profile in two different isothermal steps. For each one, we calculated the temperature and used the diffusion coefficient relative to that boundary. So what we could resolve in this way, for an example like the one that I just showed with a low magnesium core and rim and high magnesium and high temperature internal portion mantle, we could calculate the time scale from the injection of the mafic magma to the eruption, so this delta T. But this delta T is constituted by two partial time scale. The time scale of the internal portion, the core dark band, which give us the storage time, or the amount of time that the crystal spend in contact with the high magnesium magma and the high temperature. And in this case give also an efficiency of mixing. And then the second partial time scale is this delta T21 of the final rim that give us the final stage of the eruption. In other case, we were able to model more complex crystal. In this case, we have 3 mafic injection. And for this crystal, we were able to model the remobilization of the sieved core from the mash. This is an anticrystal. Okay, so how we can use this to reconstruct magma dynamics? I will show you some examples. The first one is from Stromboli volcano. Stromboli is in southern Italy, is well known for the steady state activity, where the input and output, there is an equilibrium between input and output. The shallow system is occupied by a low magnesium magma, and there are continuous injection of a more mafic, hotter magma, accompanied by crystallization and mixing. So the thing is that we didn't know when the steady state activity started, so we decided to look at the previous activity, the post-pizzo activity that just preceded the present day activity, started from 1.7, 1 kilo year ago. And we also compared this with the one of the first phase of the present day activity, just to give you a bit of context in terms of composition. These are the wool rock data for the silica content for the post-pizzo. So from the base of the sequence at the top of the sequence, a clear decrease in the silicon content going through the early phase of the present day activity. And this is the range of the chemical composition of the present day activity. We focus on the clinopyroxene, and the clinopyroxene from both the post-pizzo and the early present day activity have a very complex history with composition and zoning that reflect the growth in 2 different melt domains, a low magnesium one of augitic composition, mostly represented by the core and the rim, and the high magnesium one, which is also hotter and is diopsidic in composition. And the diopsidic composition are really the marker of the more primitive, hotter recharge that we can find as a single recharge event or multiple recharge event, or the remobilization of this patchy core that we interpret as anticrystic coming from the crystal mash. In some case, crystal, they really have the mafic recharge at the rim. So we calculated the time scale for the post-pizzo in red and the present day activity in gray. We whole bunch of time scale, range of time scale from a few days up to over 100 years, and not surprising, giving the complexity of the crystal cargo. Overall, there is a very good overlap of time scale between these 2 periods, although the some peak tend to be a different range of time scale. The interesting thing is that the upper part of the post-pizzo here has record very short time scale, as we will see in a minute, because actually it's more interesting when we look at the granularity of this data in terms of the 2 different partial time scale that I was telling you before. So we have this diagram in the time scale, and then this is the stratigraphic sequence, the base of the post-pizzo, top of the post-pizzo, and then the present day activity. The blue symbol refers to the time scale of the rim, so the time spent in contact with the last magmatic environment, which in this case is the low magnesium one. The yellow symbol refers to the internal portion of the same crystal, so the time spent in contact with the high magnesium hotter magma. And we can see that this time is much shorter than the blue one, which means that basically there is a very rapid mixing dynamics. The mafic magma arrive in the system, get mixed very quickly, and then the crystals spend some larger amount of time between 1 year up to 100 years in the system before the eruption. This, if we look at now the orange symbol, they refer to the mafic rim, and they range from few days, well, from few hours actually, up to a few months, and they really give us the timing of the triggering of the eruption. So putting things a bit together, we were able to pinpoint the trigger of the eruption. and then, but also the mixing event, which we timescale between few days to 1 year, and then the time from mixing to eruption. We were also able to determine the time scale of the remobilization from the MASH from 1 year to 50 years. And then in some case, we were able to determine the ongoing mixing, so crystals that were still mixing while they were erupting. And this is dynamic, after all, is very similar to what we see to the present day activity. So what we can say is that this period really signaled the starting of the steady state activity at Stromboli. But how this time scale compare with the present day activity? So in this study, in particular, the PhD thesis of Di Stefano, we look at the present day period, the period between 2003 and 2017. During this period, there have been two major events, explosive event at Stromboli, the so-called paroxysm in 2003 and 2007. And then there have been also, well, clearly the normal Strombolian activity, but other major events. The major event are an explosivity in between the normal Strombolian activity and the paroxysm. So what we can see here from the variation of the mg number of the wool rock is a cyclicity of the major element, where we have a couple of mafic recharge, one with the 2003 paroxysm and the other one with the major activity of 2017. And then it's followed by mixing and homogenization. The system regained the previous composition before the recharge in a very similar way to what we have seen from the post-pizzo. When we look at the clinoparoxene, again, we have a sort of bimodal composition with augitic composition here, which have also are also in the low temperature domain. But the augitic composition are mostly represented by the mantle at the rim, not from the core and the rim as before. And because the core are mostly represented by this diopsidic composition in the high temperature domain, and they are mostly antichrist. And actually, if we look at the amount of antichrist in the entire period, so here all the yellow symbol, both in the zirconium versus chromium diagram and in this schematic of the pyroxene, the antichrist are really present. Clearly, they are very well represented in the two paroxysms, the 2003 and the 2007. In agreement with the origin of the recharged magma. However, they are still very well represented in the normal and major activity, which tell us that probably, since we think that these are a portion of the MASH, that there is really a remobilization of the MASH, a quite intense remobilization of the MASH. If we look at the time scale, we have time scale from a few months up to 100 years, similar to the post-pizzo. But it's quite interesting if we look just at the remobilization from the MASH, so this A2 population, where we go from a few years at the beginning of, so from the 2003 up to decade and 100 years in the 2017. So an increasing in the time of recorded by the remobilization of the MASH, which means that probably the activity is remobilizing older portion of the crystal MASH. So we really see that the crystal MASH is very well developed in this period. And actually, when if the crystal MASH is present, if there is a general consensus that the magmatic differentiation is directly connected with the development of the solidification front. So the interplay between the magma differentiation and crystal melt separation from the MASH control the composition of and textural variability of the rafted product. And in this particular case, actually control the variability of the clinoparoxene. In fact, we can see here, if we try to model the change in zirconium versus chromium with a simple fractional crystallization process here, the red line, actually we don't have a good match because the chromium is decreasing very fast while the zirconium remain almost constant. Instead, we believe that this variability is really due to the extraction of the mash from the solidification front, and we try to calculate how much of this liquid is extracted by modeling with the in situ crystallization model of Langmuir, the gray curve. And we calculated a proportion between 0.5 and 0.8, so about 50 and 80% of melt extracted from the mash. So how the evolution of the plumbing system at Stromboli look like from the 1.7 kilo year ago up to the present day activity up to 2017. Well, we can actually see the evolution of the mash during all this period. During the post-piezo period, we do have a crystal mash because we have evidence of antechrist, but overall, it seems that we have a quite clear magma pathway, a very rapid dynamic with fresh injection of mafic magma, which they triggered eruption, overall, the mafic magma do not stall in the crystal mash for a prolonged period of time. Whereas starting from 2003, we see a completely different picture, lots of antechrist that tell us that actually the crystal mash is very well developed, but it's also start to be eroded by the incoming magma. So we have a very efficient mechanism of mash disruption and cannibalization, which is going on for all this period between 2003 and 2017. So the 2003 paroxysm really is a marker of a new life in the life system of Stromboli, with a crystal mash that has been formed and now start to be eroded. Okay, so let's move to the second example that I would like to show. It's about Popocatépetl volcano, a very active volcano in central Mexico, characterized by dome building phase, the present day activity, and the disruption of the dome. But in the past, there have been several big Plinian eruptions of different magnitude. And what we were interested in this paper that actually is led by Martin Mangler, and it's been just accepted in geology. So watch the space. In this paper, we were looking at the relationship between the magma recharge and the eruption style and magnitude. So we selected 4 different Plinian eruptions from 23 kilo year with different magnitude, here all in dark gray, and 3 effusive eruptions in light gray. The orthopyroxene population show a very complex zoning pattern with single or multiple mafic bands and a variety of evolved and mafic core at various stages of diffusion that really is the result of complex hybridization process and mash remobilization in the vertical extended transcrustal plumbing system. So we look at the time scale. This is an example from the Plinian eruption from 23 years ago. In this cumulative frequency vector time, we have range of time scale from few days up to 100 years again. But in this case, the time scale are mostly dominated by a very few data at longer time scale, more than 20 years, that they kind of obfuscate the high frequency of mafic recharge at shorter time scale. So in order to kind of see this higher frequency of mafic recharge, Martin calculated a parametry, a density parametry D, and that is calculated as the slope between 2 neighboring data point in a cumulative frequency plot. So setting a threshold of D equal 1, all the points that have D less than 1 are reported here in blue, and they belong to this tail of long time scale, and we believe that they represent the background activity, low recharge of background activity, whereas the all points that have D major than 1, they represent the mafic recharge, and they represent the priming of the eruption. We could discriminate different discrete episodes of mafic recharge. So if we look at the 7 eruptions that we studied. Here we have the 2 Plinian eruption with VI6, 2 Plinian eruption with VI4 and 5, and the 3 effusive events. So the background activity is reported in blue, and the priming of the eruption is reported in red. What we see here is a very good correlation between the priming duration with the magnitude of the eruption and also somehow the style. So particularly the largest Plinian eruption, VI6, they have priming duration between 25 and 100 years. Whereas the VI405, they have shorter priming duration between 15 and 90 years, and the effusive eruption have the shortest time duration between 9 and 13 years. Now, what this means in terms of the style of eruption? Well, the shorter priming duration that we see for the effusive eruption, they have been linked by Antonio Costa in a paper. In a modeling paper, Antonio Costa noticed that the short remobilization timescale are linked to higher crystallinity and bulk viscosity, which has been suggested to favor effusive eruption because it reduced the ascent rate and enhanced magma permeability. So we do have higher crystallinity for the effusive, for the lava flows, and we also have shorter remobilization time. So we believe that this combination can actually favor the effusive eruption. When we look at the priming duration and pattern of recharge for the two different explosive eruption, actually things are quite interesting in this case, because if we look at the high intensity Plinian eruption, the VI6, we do have longer duration, but at the priming, so the mafic recharge stop around 1 year before the eruption. So this means that basically at some point the mafic recharge stops and the eruption is driven by crystallization-driven volatile solution. So second boiling is actually the primary mechanism that triggered the eruption. We have a completely different triggering mechanism when we look at the VI4 and 5, where we have lots of mafic recharge starting about 20 years before the eruption, but they continue up to the few days before the eruption. So in this case, we really have a magmatic trigger for the VI405, which is a big problem when we try to discriminate between the intensity of the eruption. We can quite good discriminate between the effusive and the explosive, but when we try to discriminate between the few explosive, I mean, we can see from the time scale, but it's quite difficult if we're trying to interpret monitoring data in this sense. Another thing that is interesting is the background activity. So the background activity, we have low intensity of mafic recharge, and we believe that this, in this case, we don't have any evidence of major eruption during this period. So this background activity is not leaving a proper record in the stratigraphy. And it's quite similar to what is happening to the present day activity today, where we have a volcanic explosion that produce ash, but they don't leave a major record, or it will be very difficult to discriminate between the different volcanic explosion. So this means that actually we really need to pay attention when the current activity, style of activity will end at Popo, because this means that then the systems start to be primed for an eruption. The last point that I want to make here on this particular study is that if this characteristic relationship between the priming of an eruption and the magnitude and style of the eruption is proven to be true for other systems, for other volcanoes worldwide, but probably we have a tool or the opportunity to improve our ability to forecast volcanic eruption. The last example that I would like to show you is the recent work done by PhD student Gerard Hughes on Colima volcano, another big and active volcano in Mexico, characterized by activity quite similar to Popo, where we have dome phase growth and associated with destruction of the dome with some major explosion and PDC. There are also lava flows associated with these. Gerald, look at the activity between 2013 and 2017. And divided these in 6 periods, in 6 eruptive phase. Phase 3 here reported in red is a special one because it's made only by a single eruption, an explosive eruption, which is the major explosive eruption occurred at Colima in the last few years. Again, we concentrate on pyroxene. You can probably tell now that pyroxene are my sort of obsession. We found different population as usual, an homogeneous one. The chemical composition is reported here in the pink field. So this is just the magnesium number versus the core boundary rim of the crystal. Then we have 2 different population, a normal zoned 1 and a reversed zoned 1. And in this we can see, we can characterize the mafic recharge. It can be a single mafic recharge or multiple mafic recharge, or clearly the mafic recharge at the rim for the reversed zoned. And both population have the they do have some crystal with a mafic core here, reported here, which really is the remobilization again from the MASH. Using the 2 pyroxene thermometer of Putirka, Gerard was able to calculate the temperature for each of the portion of the crystal, and this is the temperature that we use in the time scale to calculate the time scale. He was also able to produce a sort of calibration curve, temperature versus magnesium number of the pyroxene, identify a mafic end member and an evolved end member. So looking at the time scale, this is reported for just showing the time scale for the 3 phase 2, phase 3, and phase 4. The phase 3 is the one that has the explosive, the 2015 explosive eruption, and soon after there was a lava flow following, which made up phase 4. Since we know the age of this eruption, clearly we can transform the relative time scale in absolute age, giving a chronology of the eruption. From the density of the time scale, Gerard was able to identify mixing event, here reported with this black arrow and red arrow. So for the phase 2, there was one mixing event, one major mixing event about 180 days before the eruption. For phase 3, we have 3 mixing events, one about 6-10 months before the eruption, so between September 2014 and January 2015. Another one between 1 and 4 months prior to the eruption. The last one, a cluster of time scale, few days before the eruption. If we look at phase 4, we have a mixing event few days before the eruption that actually overlap with the mixing event. Actually, both these events overlap with the mixing event of phase 3. We also have some overlapping between some time scale, a mixing event between phase 3 and phase 2. The overlap of this mixing event led us to believe that these are probably the same mixing event. So we have remnant of an early recharge event in the magmatic system. And this was already something that has been noticed in other volcanoes like Ruapeo by Kilgore, a collaborator in 2014. And why is important this? Well, because first of all, it's really important to try to know how many recharge event or mixing we need to have to prime the eruption. And then it's important to discriminate if the mixing event that we are seeing is a new one or is a remnant from the early recharge event. And this is critical when we look at the trying to combine the time scale with the monitoring data. This is what Gerard has been doing for his PhD thesis and for the manuscript that he has in preparation. Here we have the time scale and then all sorts of monitoring data. There is not that much correlation between the time scale and the monitoring data in 2014, but comes to the 2015 and the building up to the explosive eruption, we really have a very good agreement between the mixing event and the increasing in explosion in LP signal, in tremor, and also in the SO2 flux, which pick up and then remain quite high for the entire period. So in terms of the system, what we see is that probably there's a frequent injection really prime the reservoir, determining a lower viscosity, which promote a volatile separation, and then the ascent of volatile ahead of the magma body, which result in mixing and is and then is followed by is determining all the monitoring signal that we see, the peak in XO2 flux, and then all the other seismic signal, until then the system is primed for the eruption by the continuous injection of the magma. So just to conclude, few final remarks. I hope that's it's quite convincing that resolving the chronostratigraphy of the diffusion chronostratigraphy is quite powerful to understand magma dynamics, trying to setting robust constraint on the rate of magma mixing, the mass remobilization triggering events. At Popocatépetl, we have a case study in which we can see that the magma recharge pattern really controlled the eruption style and magnitude, and this also helped to clarify the triggering mechanism for different eruptions. And if similar correlation are proven to be more widespread, probably we really can improve our forecasting ability. And finally, when we reconstruct the time scale and the frequency of recharge event that prime a magmatic system, really, this is very important implication. It's very important when we look the time scale associated with the monitoring data. And with this, I stop and I thank you very much for your attention. And I'm happy to take any question.
Thank you, Chiara. That was a very nice overview of a few different applications of the tool. And I didn't know exactly what you're going to speak about when the program was set up, but I think nicely ties into what is coming up next in terms of triggering mechanisms and looking at things. But before we get to that, I'll ask people here, are there questions? You can type things into the chat or just unmute yourself and ask things. People usually take a minute to say this. I'll give you
a question. Yeah, so first of all, that was really interesting work, as always, by you and your students. I have a question particularly about that last part of the talk, the Kalima stuff. How can you or your student determine those distinct mixing events? In particular, I'm referring to phase 3, but that you kind of determine these 3 distinct mixing events. But to me, it looks like there's this continuous distribution of diffusion timescales, and each one of those have significant error bars that overlap with one another. It's hard for me to, I guess I just want to know, how do you distinguish 3 distinct events rather than just sort of a start and a stop?
Yeah, no, thank you. That's a very good question, actually. Yes, there is a significant overlap. Maybe, I don't know if better if I reshare my screen.
Able to? Go ahead.
Okay, so yeah, there is a significant overlap here. But for example, this very short time scale, you can see actually they really don't overlap. And in a similar way that we did for Popo, if you look at the neighboring, at some point you really can start to discriminate. Clearly, I mean, this is probably more, probably the injection are more continuous, but seems that there are sort of clustering in a few periods, like these periods, and then these other period, they're really clustering together. Here are more sparse, and then the last final time scale that are really kind of more timed together. Yeah, I agree. I mean, it's probably these need to be refined better, but seems really that we can really have a clustering of events. Probably we need to run some statistic data on these, a bit of statistic as Martin did for the POPO to discriminate better. I don't know if this answers your question.
Yeah, it did. And I really liked how in that other study you did the sort of slope between different points. And I can see how if you were to do that with this data set, it would probably show 3 different mixing events. So I like that approach. So
yeah, this is the next task for Gerald to do, actually. He was busy in trying to finish his PhD. Actually, he's discussing his PhD in 2 weeks' time. So he was really busy trying to finishing, and so it's not refined as should be. But yeah, I mean, that's the way we are going.
Great, thank you.
Okay, so on the chat, I have a comment. Somebody's congratulating from Venezuela. Rafael Rosales was excited by your talk. And I see Maren has raised her hand. So Maren, if you want to unmute and
yes,
on screen and ask your question.
Yes, thanks very much. Thanks, Chiara, for this very nice talk. I have a question. When you show basically the cumulative plot of the time scales for different eruptions, you basically observe that towards eruption onset, the time scales seem to speed up or accelerate, right? And you were mentioning in some cases that this is related to different intrusive activity. And I was wondering if this is intrusion into a mush pile, and this is very much related to a paper of Cheng et al. 2020, if the range of timescales could also be explained in terms of that, depending on where the crystals were located in the mush pile, they may have experienced the intrusive event at a different time, and therefore you get basically this array or range of timescales instead of being different intrusive events. So what do you think of that?
Yeah, no, that's a possibility. And actually we really, yes, clearly, we really thought about this. If this really represents the same mixing in terms of just like remnant, or it's kind of where the crystals are, they can kind of record a different time. It's a possibility. And it's not an easy, there is not an easy way to distinguish between these two events. I guess it's mostly depend on the dynamic of the system, what you know about the system. So it's not really coming from just one, just from the time scale, which really you cannot resolve, but trying to put together the observation from the time scale and from the rest of the crystal. So how the crystal look like and how they all the other characteristics. So for example, for Stromboli, the fact that we have a very quick dynamic of the mixing, this probably exclude the fact that we really have the crystal, they might see a different, time, but depending on the where they are in the system, but they see different, not the same event. So the paper from Cheng, what they say is basically you have an intrusion which kind of propagates up quite for significant in time. At Stromboli, we have a very rapid mixing. So we think that what we see is that crystal might not see all the same, not all crystal can see the same event, but when they see the event, it's very rapidly mixing. So it's more combining several observations rather than just looking at the time scale and deciding, yes, these are different event, or it's just a propagation of the same event. So really depends on the dynamic. If you have a more a crystal mass where you really have the pile of the crystal mass and the liquid is moving through the crystal mass, probably yes, the model of Chen et al. Is really better, will describe the system better.
Okay. Now, I should point out to people that what we do is we have a few questions, and then we have the second talk, and then we continue on with a discussion on both talks. So if you have questions and haven't had a chance to ask it, type it into the chat or hold it to yourself for later. Now, I had one more raised hand here. I'll take that, and then before we go to the second talk. So Martin Magner had something to say. So maybe you want.
Yeah, hi, thanks. I wanted to add to Chiara's answer. I agree with everything she said. I just wanted to say for the specific case of Popo, we had in each of those recharge events that we could identify, we had mafic crystals from a larger depth that were normally zoned. So these obviously represent different timescales. These couldn't have been stored in the evolved reservoir prior, in the decades or centuries prior. These were injected by the recharge event into the evolved reservoir. So by looking at those, we can identify distinct recharge events. And in fact, in almost all of our different recharge events that we identified, we had mafic crystals that basically tied those clusters to actual recharge and not mushroom remobilization.
So that provides some added constraints on the things. Okay, yeah. Thank you. That's great. So I think we'll stop. And thank you again, Chiara, for the talk. And we will.
Thank you very much.
To this, but you can try to move to the second talk today, and that's going to be a double header. So there are two speakers, Christy Till and Adam Kent. So the title is "Start Me Up: The Relationship Between Volcanic Eruptions, Eruption Characteristics, and Eruption Initiation Mechanisms." So it really just boils nicely onto what Chiara has been talking about, but in terms of a general overview. So to introduce the speakers, starting with Christy, she did her bachelor's and master's at University of California, Santa Barbara, and then went on to do a PhD in 2011 in MIT. After a short postdoc there, she was a visiting scholar in Stanford, had a Mendenhall postdoc fellow in USGS, which is very prestigious, of course. And she's been a faculty since 2014, I think, till today in ASU in Tempe. Right now, she's visiting University of Oregon State University. I have to keep the names straight. Never mix up two different universities in the same state with different names. That's what I've learned during my time in Arizona. So Christy is on a wide range of interests. She works on magma genesis, experimental petrology, diffusion, chronometry, and measurement of diffusion coefficients. She does a lot of things on subduction zones, and even works on magmatism on exoplanets. So she's very well placed to do the synthesis with Adam, who has an equally broad range, but a different set of topics. So they both do diffusion, of course, but Adam has melt inclusions and development of in situ chemical and isotopic analytical techniques. Now, to go to Adam's background, he did his undergraduate studies and graduate studies actually as well in Australia. So starting from the University of New England, where he did his undergraduate, he did a PhD at ANU. And after positions at several places, including Denmark and so forth, he has been faculty at the Department of Geology, and he's a professor of geology and geochemistry at Oregon State University in Corvallis. And he, in addition to being a faculty, he is also a director of the Keck analytical facilities. And how they're going to split the talk among them is up to them. So I'll just hand it over to Adam and Christy with that. It's all yours.
Thank you so much, Sumit. I'm going to start us off and then I'm going to turn it over to Adam. So thank you everybody for being here today. It's morning here and the sun just came up in Oregon where I am at the moment. And the title of our talk is Start Me Up, the relationship between volcanic eruption characteristics and eruption initiation mechanisms. And this is a study led by Adam and in collaboration with myself and Carrie Cooper at University of California, Davis. Next slide, please, Adam. So with the exception of a relative minority of open system volcanoes that persist in an eruptive state, most volcanoes spend their time not erupting, something that we can observe nicely in this overview figure from the USGS for Cascades volcanoes. We see here on the right, these little volcano icons show us the eruptive phases for each of these volcanoes, but the majority of the time they're sitting there in quiescence. And they summarize this talking about how active periods last for a few years to centuries, but the quiet periods are much longer, of a few decades to thousands of years, and such that volcanoes erupt infrequently. But the question then is, next slide, please. What are the particular things that cause volcanoes to begin erupting then? Essentially, we say what initiates volcanic eruptions. Here are two beautiful examples from Mount Pinatubo and Mount St. Helens, both of which were sitting in quiescent periods before cataclysmic eruptions that we are seeing beautiful images of there. So what kicked these volcanoes into action is sort of the topic or the focus of what we'll be talking about today. Next slide, please. And somewhat surprisingly, this is a rather underexplored topic in our literature. You can look at the seminal work, the Encyclopedia of Volcanoes, and there is no chapter devoted to what starts eruptions in this seminal reference, nor is there much of a discussion at all in any of the constituent chapters about what starts eruptions. And so find ourselves needing to think about this in a bit more detail. Next slide, please. So in the work that we're presenting today, we have chosen sort of an explicit set of definitions here because we find that when used in the literature, we see the words eruption initiation, eruption trigger. We heard a beautiful example in Dr. Petrone's talk of many terms that are associated with this, and also including priming. But we see the need to state some explicit definitions for use here. So for this talk and this body of work that we're presenting, we're using eruption initiation to define the process or processes by where magma that's stored in the crust in a stable or quasi-stable state begins to commence to move upward and eventually erupt. And this is in contrast to something like we might say as an eruption trigger, and that might be something that we for example, relate to processes that happen within an eruption, syneruptive processes like effusive to explosive transitions, or within the shallow part of the magmatic system. So Mount St. Helens provides a nice example and context for these definitions. So the specific eruption itself on May 18th, 1980 began or was triggered by a magnitude 5.1 earthquake and the associated landslide. But what initiated the eruption and caused magma to begin move upwards and build the cryptodome occurred several weeks earlier or months earlier. So that's the context for which we'll be using these terms today. So the overarching questions that we're addressing are, what are the mechanisms that initiate volcanic eruptions? And how are these recorded through petrologic evidence specifically? Can we identify volcanoes that consistently initiate eruptions and these specific mechanisms? And are there relationships between these initiation mechanisms and observable volcano monitoring records? This is all sort of in working up to the question of asking, is there predictive power in knowing past eruption initiation mechanisms for volcanic systems? Next slide, please. So we know something about the physics of how eruptions are initiated. Here I'm showing a nice figure from de Gruyter et al. 2016, and that builds on a body of work started by de Gruyter and Huber in 2014. There's been other important work in the literature about the physics, which basically the sort of idea is that we are initiating an eruption by having a critical overpressure reached in a magmatic accumulation of some kind, and that this drives a crack to be propagated so that we can ascend magma through the crust. So this overpressure puts the surrounding crust in tensile failure, and so you have a little schematic here where we're seeing magma injected into a reservoir over on the left, and then modeling the associated overpressure with each of those injections and the amount of time that it takes to accumulate that overpressure. And when in this study, they see a critical overpressure of 40 megapascals is reached, then they interpret that, and that is the critical threshold and with which it was necessary to produce the eruption. And different crustal stress states and rheologies are going to change the sort of parameters at which a critical overpressure is reached. But this is sort of the broad physical framework in which we might think about initiating an eruption. Next slide, please. And so we need to take that sense of physical mechanisms that initiates eruptions and put it in the context of these transcrustal magmatic systems that were nicely illustrated in the previous talk, where we have bodies of both liquid and crystal mushes, exolved fluids, and different composition liquids. And they're complex in terms of their physical and thermal structure, composition, and crystallinity, and their volatile cargo and rheology. And so we need to think about what is the specific mechanisms then that produce the overpressure in these systems, and what is the evidence for them. So I'm going to turn it over to Adam to discuss those specifics now.
Great, thank you, Christy. I hope everyone can hear me. If not, the only person I can see is Christy. So if she tells me she can't hear me, then I'll listen to that. Yeah. Following up from that, thanks. We're going to talk about this subject from mostly a petrological perspective, and obviously petrology is not the only discipline that would have insight into initiation of volcanic eruptions, especially modern eruptions that we can observe with an instrumental record. But we feel that petrology is really an underutilized tool to studying this problem, and there's a very petrologically rich record about the processes that initiate volcanic eruptions, much of which perhaps remains underutilized. We saw in Chiara's talk just before excellent examples of how petrology, using petrological techniques, can give us some insight into both the nature and the timing of volcanic of eruption initiation. And partly petrology is so rich here because initiation of an eruption is probably the last set of important high temperature processes that happen to a magma. So the preservation potential is excellent. The obvious example there is crystal rims. It's much easier to understand what happened to a crystal looking at the rim. The context is very clear. It's the most recent thing happened. Than if you're trying to dive deeper into the eternal part of a crystal and figure out some event that may have happened earlier in the magmatic history, but is obscured by successive events. And so there's a lots of and we'll be primarily talking about petrological observations in the rest of this talk. And there are a lot that can be made, ranging from sort of outcrop scale zoned eruptions, or even map scale zoned eruption observations. There are things like banded pumices and mafic enclaves. There are sort of observations related to juxtaposition of crystals of different origins, zones of individual crystals, and then also breakdown rims of some minerals that become unstable during magma ascent. and also intracrystal features like other zoning, or also magma and fluid inclusion. So there's a sort of the take home here is there's sort of a rich petrologic record here to understand the processes that initiate eruptions. Also, the beautiful thing about working with actual physical samples is it not only allows us to understand recent eruptions and tie it in perhaps with a monitoring or a geophysical record, but then also to look back through time and try and create a sort of a time history of an individual volcano or volcanic system and how eruptions have been initiated. And finally, also, again, with Dr. Petrone's talk, we saw before this, we can get a lot of information about timescales. This is a diffusion seminar. I cut the only slide that had diffusion information on it, sorry. But a lot of the timescale information we have comes from diffusion studies. And the great thing is that the number of these in the literature are increasing rapidly. And also there are other kinetic phenomena which can be used, things like crystal growth rates or the rate at which fluid inclusions or melt inclusions re-equilibrate. So we also get a lot of information about timescales. So sort of the primary data set I'll be talking about is a meta-analysis, a sort of summary and compilation of initiation mechanisms that we've been able to identify from the literature. We have a compilation which consists of 73 studies, 73 eruptions, sorry, of 40 volcanoes, which are mostly dominated by subduction, but include mid-ocean ridge and intraplate as well. These studies either implicitly or explicitly state what they believe to be the eruption mechanism, or in some cases prevent enough petrological evidence that we are confident in making our own interpretation. So we've compiled those, and then what I'll be showing today is the result of that compilation, sort of our breakdown of different eruption initiation mechanisms that we see petrological evidence for, and then finally some statistics to try and explore whether these initiation mechanisms, different initiation mechanisms, are related to differences in other volcanic features. So this is sort of cutting to the chase here, but this is sort of the classification of initiation mechanisms we have come up with. And I'm not really the greatest at making good looking PowerPoint slides, so I'm sorry if this is not like aesthetically that pleasing. Basically, there are two families of eruption mechanisms that we can see. And it's important to recognize that we are dealing with eruption mechanisms that we feel that we can identify through petrological techniques. And so we have to also be aware that there's a possible bias here with say, eruption mechanisms that may leave a very subtle or almost or no petrological record. So that's just something to be aware of, but we're dealing with the petrological evidence here. The two families that we see are those mechanisms that are related to addition of new magma and those that are not related to addition of new magma. I'll start with those first. And so the general category that we have for those is vapor accumulation or second boiling. This is where pressure is increased by vapor exsolution or vapor transfer to promote overpressure and eventual eruption. Another category, a sort of a general category of mechanisms. I'm just going to give myself a pointer here. Are shown at the bottom here, and this is just again this family of mechanisms that may not leave a petrological record or a subtle record, such as buildup of buoyant forces, roof failure, or even far field triggering of an eruption or initiation of eruption via things like earthquakes or other tectonic forces. But and the percentages here show the percentage of our compilation that fall into each of these categories, and so you can see that the vapor accumulation is a relatively minor part of it, only 7% of the compilation. Majority of things we've been able to identify relate to addition of new magmas, and we can break that group again down into two categories. One is where there is a significant contrast in magma composition. So the magma that is being added to some sort of magma reservoir is significantly different in composition to that which is already there. And so we're calling that process recharge. The contrast of that is when there is addition of magma with a minimal compositional contrast, and we call that rejuvenation. Obviously, these are arbitrary uses of this nomenclature, but I think one advantage to the whole community that we could do is to start use more well-defined nomenclature for these processes, so we know we're all talking about the same thing when we use the same words. So we've elected to use recharge and rejuvenation, and we separate these out because the possibility that quite different physical processes operate to initiate an eruption. With rejuvenation, either mafic magma entering a mafic magma reservoir in the case of mafic rejuvenation, or silicic felsic magma entering a silicic reservoir in the case of silicic rejuvenation. The lack of compositional contrast may mean that initiation is more related to an internal increase in pressure by adding magma to what is, if you add it more rapidly enough, it's essentially a fixed volume. Whereas we're talking about magma recharge, and that's primarily mafic recharge, which is addition of a mafic magma to a silicic reservoir. The converse may exist, but there are no examples of silicic recharge that are. There is one possible example, but it's not uniformly agreed in the literature. So, but the addition of mafic magma to a silicic resident magma, the large difference in physical properties of both those magmas may result in additional physical processes to initiate eruption, such as exsolution of volatiles and sort of the classic underplated basalt generation of foam, those sort of processes. So I'm going to very quickly just go through each one of these four: mafic recharge, mafic rejuvenation, silicic rejuvenation, and vapor accumulation, and talk about what the evidence the petrological evidence we see for those is. Mafic recharge is addition of mafic magma to an intermediate or an evolved reservoir. And I didn't make the point that I probably should have in the previous slide, that the difference between mafic recharge, or between recharge and between rejuvenation, it actually lies in a continuum. So it's one of these situations where we have to put a division in something that's probably a continuum. And perhaps that means that individual interpretations between different workers on those might vary. And I think we're at the point in this study where we would invite different interpretations. I think the important thing is that we start to look at eruption initiation mechanisms. And I'm not saying what we have done in this particular study is 100% correct. There's a level of interpretation with some of it, but I think it's important that we start to look at these sort of issues. So mafic recharge, addition of mafic magma to an intermediate or evolved mush. It's very common in subduction-related stratovolcanoes. For a start, there is a significant composition or a thermal contrast between the magmas. The petrological evidence are what I call mafic mineral rims. So this might be a mineral such as plagioclase, particularly a mineral that had, like plagioclase or perhaps pyroxene, that has a fairly elongated phase stability, that have rims that are consistent with addition of a very different magma composition. And so an example is shown here from some of Madeline Humphrey's work on Soufriere Hills, where phenocrysts, plagioclase phenocrysts in these gray symbols have much lower iron concentrations than phenocryst rims, and also by microlites. So the interpretation is that the rims and the microlites grew from a more mafic magma, which recharged to silicic magma and initiated eruption. You can also see juxtaposition of mafic and silicic mineral populations. And by mafic and silicic minerals, I mean those that form minerals that form in either a demonstrably mafic or demonstrably silicic magma. You can also see the classic disequilibrium mineral assemblages, such as, the juxtaposition of olivine and quartz is a classic one we often use in our classes. There are things like enclaves and banded pumices, which also give us direct insight into the fact that two magmas of significantly different composition have been juxtaposed. You can also see this occasionally in zoned eruptions where both compositions end up being erupted. And finally, the large thermal contrast related to mafic recharge can also produce significant mineral dissolution. So then moving to the first type of rejuvenation, I'm not going to talk about silicic recharge because there are very few examples in the literature. All the examples that we have in our compilation are ones where we were also able to have an estimate of timing. So that was sort of limits the number of studies we have, but also makes it more powerful because we have that information. So silicic rejuvenation, addition of a hotter silicic magma to a less hotter or perhaps more crystal-rich silicic reservoir or mush. And you'll find silicic rims on silicic crystals. And again, sorry for that nomenclature. It just means crystals, in this case, like quartz or alkali feldspar, which are going to form much more commonly and have phase stability relevant to silicic magmas or to felsic magmas, growing rims on them that show intrusion of a magma that is of broadly similar composition, perhaps slightly hotter, and perhaps by slightly hotter, I think in the paper we draw a line at somewhere like 50 degrees. Maybe it's slightly lower than that. So indicative of a thermal contrast, but a much more subtle thermal contrast than when we're talking about mafic recharge. You can also see mixed populations of minerals like quartz and alkali feldspar, although again, it can be more subtle because of the lack of major compositional contrast in the intruding magma and the resident magma. You can also see examples of of crystals that formed in a, or that were previously resident in a mush that was subsequently remobilized. And this occasionally is also evident in things like cryptically zoned eruptions, where crystallinity is for instance, is the main factor that is zoned through an eruption. The example I show here are just sanidine crystals from some of work by Hannah Shamloo and Christy from Lava Creek Tuff that show these nice barium rims. Though Christy and Hannah determined that they are equivalent to an increase of perhaps 20 degrees Celsius related to intrusion of a rhyolitic magma into a rhyolitic mush that occurred maybe a few decades before this eruption. So the next is mafic rejuvenation, which is very common at basaltic volcanoes. In fact, for all the eruptions that we have in the compilation that are basaltic, with the exception of one, appear to have been initiated by this process, which is very similar to silicic rejuvenation, except it's addition of a somewhat hotter, perhaps and presumably less crystal rich mafic magma into a mafic reservoir mush. And Dr. Petrone in the previous talk showed some excellent examples of this. So again, this can be seen by rims on mafic minerals, such as a reverse zoning on olivine is the classic example, or also on pyroxene. You can also see mixed populations of mafic minerals, or presence of minerals such as the strained olivine crystal here from Kilauea Iki from work by a student of mine, Richard Bradshaw, from a few years ago, that show evidence, in this case, the internal deformation of being present, of being deformed within a crystal mush prior to being reactivated and erupted. And again, even though we're dealing in overall a higher temperature situation, we see evidence for more subtle or more limited differences in temperatures between the intruding magma and the resident magma. So those are the three mechanisms related to addition of new magma. And then the final one is volatile accumulation and boiling. And there's a number of, actually, this is sort of a collective for a number of potentially different processes. One is the classic second boiling that can occur to increase internal pressure. Another is transfer of volatiles from somewhere else within a magmatic system. Another one perhaps is assimilation of volatile rich wall rocks. All of these have been recorded and interpreted in the literature. Some of the evidence, petrological evidence that you see will be changes or melt in fluid and compositions as you approach crystal rims. You can see changes in hydrous mineral compositions that will reflect changes in the amount or the composition of a vapor present, so minerals like apatite or amphibole. And occasionally you can also see increases in what I call vapophile elements that will be transported in a vapor, such as lithium, in minerals or melt inclusions. And the example I show here is actually from Mount St. Helens in 2004, where progressive eruption of a dome occurred, and plagioclase from the very earliest phases of that dome had very elevated lithium concentrations, which in one of my papers interpreted as a result of accumulation of a lithium-rich vapor phase or volatile phase, sort of at the upper part of that magma reservoir that eventually produced an overpressure that initiated that eruption. So then looking a little bit more at our compilation, I showed these percentages again. Actually, they're slightly different here. I'm sorry, because the compilation gets continuously updated. But in addition to understanding the eruption initiation mechanism, we're also able to track other things like eruption style, composition of erupted material, eruption timescale, and erupted volume. And we were interested in understanding whether these factors, these parameters, change systematically between eruptions that are initiated by the different mechanisms that we feel we can recognize. So the approach we used is one that perhaps is less common in our field, which is fairly quantitative, and that's one of categorical variables. So we're not dealing with variables here that are continuous. We're dealing with variables that we can place into a category, such as, if you're unfamiliar with that, think about the difference between the height of a group, the differences in height of a group of people that you can measure, and it sort of falls in a continuous series of numbers, versus whether they have brown eyes or blue eyes, which is just you either fall into one category or the other. So we've elected to do this for all our variables that we've tracked. And the reason is it's a great way to deal with large uncertainties. For parameters like eruption timescales, even though great effort, or we've made great achievements in making these more precise and accurate, there's still relatively large uncertainties. And it's not uncommon to see estimates of, and I think Dr. Petrone in her talk said an estimate of something like between days and years or days and centuries. So dealing with a number like that on a continuous scale is not particularly practical. So for and erupted volumes are sort of the same. We don't really estimate erupted volumes with enough fidelity to make it that useful, treating them as a continuous variable. Anyway, for all the eruptions, we've placed them in the categories. I'm showing the categories that are shown here. So for volume, for instance, less than a kilometer cubed, 1 to 10, 10 to 100, or greater than 100 kilometers cubed. And I would be the first to admit that we could probably be more sophisticated and more detailed here, except we also have to understand that we're not dealing with a huge amount of statistical power here. We only have 70 individual eruptions at the moment. So if we can continue to add to our data set, we can then continue to try and pick this data apart in more detail. But at the moment, that's not feasible. Then also, to simplify the statistical testing, I actually made it even more simple and worked out a sort of what's called a dichotomized categorical scheme for each variable. And that's just considering only 2 categories. So in the case of volume, it's less than a kilometer cubed or greater than a kilometer cubed. And that just simplified the first order statistical testing that we're doing. And so we did this for each of our categories, either for time scale, months or less, years or greater, eruption type, extrusive or explosive, composition is as well. And of course, there comes another level of interpretation here with you have eruption that starts perhaps with a modest explosive phase and then is largely extrusive. And we just tried to capture that, which was the most volumetrically important for an eruption. And so this is just some of the results in a histogram. Each category is sort of percent of total for initiation timescale and eruption scale. I don't want to go into the details of these too much. I just want to show that between different eruption initiation categories, to the eye, there appears to be some differences in the, say, in the relative proportions of explosive to eruption. There are many more extrusive eruptions initiated by mafic rejuvenation, for example, than felsic rejuvenation, which has more explosive. And the same in timescales, even though it's broken down, just even to the eye, I hope you can see that the pattern between different eruption initiation mechanisms that we identify is different. So then the question we want to ask, are these differences actually statistically significant? And the reason we want to ask that is because, does this mean there's something there with this? Does it mean that if we know the eruption initiation mechanism for a volcano and perhaps we track that through time, like we might track eruption style for a volcano through time, would that give us some sort of predictive power for future eruptions? And so this is the first step to trying to sort that out. So the way we're doing this, we're basically testing it for all these histograms. We're testing the null hypothesis, and the null hypothesis that no difference in proportions exists between eruption initiation mechanisms. And so categorical variables, there's a number of statistical approaches that you can sort of borrow from the social or the biomedical or the medical sciences for this. The one I'm using here is one that is good for relatively low amounts of data. It's called the two-tailed or the Fisher's exact test. It was actually invented by an English vicar to determine whether it was possible to tell whether you poured milk into your tea before you poured the tea in or after you poured the tea in. And it's hard for me to think of anything more English than that, actually. So that's why I like to tell that story. Anyway, it was invented in the 1930s. It's basically a way to test these things called a contingency table. So I show an example of a contingency table here. This is just for eruption timing. Our eruption initiation mechanisms are shown on the vertical set of columns, vertical column here. And here across the top are our 2 different categories, like months or less, years or greater. And then we just simply the number of eruptions that fall into each category. What we are testing, or what the Fisher exact test lets us calculate, is a probability of generating this observed distribution if the null hypothesis is correct. So that means if you generate a probability that getting this distribution is very low if the null hypothesis is correct, it means that the null hypothesis is less likely to be correct. And if you falsify the null hypothesis, that means there are significant differences between different eruption initiation mechanisms, in this case, in terms of scale. So there are a couple of different ways, and I won't go into the details of how to apply this, but here's the result of, say, the 4x2, so contingency tables like this, where we do it for each of our 4 parameters for time scale, volume, composition, and eruption style. In all these cases, the p-value is low. And if you know, there's this a debate at the moment about whether strictly, you know, in the past people have applied a p-value of 0.05 essentially 95% confidence as a measure of statistical significance. I think now more and more people are looking at that as not so much a hard and fast, if it's below 0.05, yes, if it's above 0.05, no. But this gives us at least an impetus to think there is some value here and that we do have some predictive power, that the differences we see are not purely random, but we do see significant and consistent differences between these different eruption parameters that we've tracked and the eruption initiation mechanism. And that's what we interpret these low p-values all to mean. We can dig into it a little deeper, and this is just a summary. I realize there's a lot on here, so don't feel like you need to read and digest it. I'll tell you about it. This is, again, a contingency table summary, but it's a contingency table where we just compare pairs of different eruption initiation mechanisms. So felsic rejuvenation versus mafic rejuvenation. Wherever you see something bold, it means that the p-value is less than 0.05. So there's good evidence here that we can maybe use this to generate some more additional hypotheses that we can test, or that there is reasonable evidence there's some sort of, that we can reject the null hypothesis. There's some sort of relationship here that, for example, in the case of comparing felsic and mafic rejuvenation initiation mechanisms, there are differences in timescale, style, composition, and volume. And of course, some of those make complete sense. Felsic rejuvenation is going to produce a different composition than mafic rejuvenation because you're adding felsic magma to a felsic resident magma versus adding mafic magma to a mafic resident magma. So that's you would hope to get a different composition out of that. However, things like eruption timescale and style and volume are still not, they're not controlled by that. So it's still a lot of interest here. An underlying value just means the p-value was low enough, in this case less than 0.4, to perhaps also say that there's some additional interest in pursuing this more, maybe with an increased data set or with more targeted and different hypotheses. And the example here is, this is just an example again of one of these contingency tables, and this is just a 2x2 contingency table. So just directly comparing felsic rejuvenation, mafic rejuvenation in terms of timescale. The reason why the 2x2 contingency tables are done here is they're actually computationally much easier. Once you get up to larger contingency tables, you actually have to do it using sort of Monte Carlo approximation methods, where you can actually have an explicit, you can generate an explicit answer, explicit p-value for a 2x2 contingency table. And I think this is where I hand back to Christy, correct?
That's right. Thanks, Adam. So Adam's done a really nice job of showing us that there's statistical differences between these different eruption initiation categories that we have defined here. And they're shown schematically on this figure at the bottom, arranged from mafic rejuvenation, so mafic into mafic magma, mafic recharge, mafic into silicic magma, volatile accumulation, and felsic rejuvenation of silicic magma into silicic magma here on the bottom. And so these categories that are illustrated in the arrows at the top we've shown that there's statistical differences in these eruption characteristics between these different eruption initiation mechanisms. And if the statistics went by a little bit quick, no fear. So the hope is to sort of illustrate the overall trends that we see in those eruption characteristics up here on the top. So we see that overall explosivity is statistically different and increases to the mechanisms to the right. We see that erupted volume is statistically different between these different categories and increases overall as we head to the right. We see that erupted composition is statistically different between these different initiation mechanisms and proceeds from more mafic to more felsic as we go to the right. We also have seen that the eruption initiation timescale, so these are ones determined predominantly from the diffusion chronometry that we are familiar with, but also from other kinetic mechanisms that Adam mentioned at the beginning of the talk, things like melt inclusion reequilibration, are statistically different between these different categories and show different time scales that go from shorter on the days time scales over to average of decades or longer over on the right. And that also one thing we haven't mentioned, but we see that run-up timescales. So those recorded from monitoring data of volcanoes from geophysics and remote sensing, the timescales of those prior to eruption also are different and proceed from shorter over on the left to longer over on the right. And this summary figure and all of the data that we're presenting today is available for download from the Earth Archive preprint server, and the link is provided here, and we can put it in a chat or share it via email. Can you go back one slide, Adam? I won't go into this at length in the interest of time, but another thing that we were able to show is the relationship between the diffusion timescales and the monitoring timescales measured by what we're calling run-up timescales from geophysics or other methods. And we don't have geophysical observations, obviously, for all the eruptions, especially many of the eruptions that were in the study that were before modern times. But for those that do have observable monitoring data, we've been able to look at that timescale in comparison. And you can see, particularly for mafic rejuvenation, where we have the most data, that there's a relative agreement of these timescales from diffusion, plotting along that 1-to-1 line down the center. But there also seems to be some offset, some mismatch between the run-up timescales and the initiation timescales. Especially this is well illustrated for mafic recharge, where we have a number of studies where the monitoring signals start before the diffusion timescales up to the top left, whereas a couple of studies where they plot where the petrologic diffusion signals precede the monitoring down to the right. So this shows the power of doing this kind of study and categorizing our initiation mechanisms and continuing to build on this work. Next slide, please. So where do we go from here? I think that this study nicely illustrates the potential for an increased emphasis of understanding eruption initiation mechanisms from our community. Because of the statistical differences we observe, it suggests that there is power in following this line of inquiry. And we recommend at the end of our work that what we need is more data, more studies to identify the specific initiation mechanism. Rather, we need better data and to reduce uncertainty as well, but the power in learning more about this and its prediction capability really comes from just generating a lot more studies that focus on these particular aspects. We need to integrate this work from petrology and eruption initiation mechanism studies with our monitoring data, and continue to explore the potential for this kind of characterization and petrologic monitoring of volcanoes could become a powerful thing in our future. So with that, we'll end there, and I'll put the link to the Earth Archive in the chat if people want to read more about it, and we're happy to answer questions.
Well, thank you, Christy and Adam. I think this is a very, very useful thing for all of us to put all our observations and results that we've been getting into some context, because I mean, you can start putting things in the context, and that's when you see what which one of these statistics stand up and how things shift within these statistics and so forth. So I think it's a very good framework for all of us to have, and for students studying onto the field. But we'll start with some questions, and Ralph had some question, I thought. No? Oh, so Ralph was just clapping. Okay, got it. So let me just check quickly on the chat. Okay, so the chat is just the message. So people can put questions into the chat or ask questions here. Massimo. Did you have a question, Massimo?
No, sorry.
Sorry.
Just to. Sorry, mine is only a reaction. I remained impressed by the last presentation, so only to make this.
All right, very good. So Philip Ruprecht, yeah, he has a question. It's a different emoji.
Yeah, thanks, Sumit. Yeah, it was a great summary. I have a question regarding the difference between recharge and rejuvenation. And I mean, for you, if I understand this correctly, you basically consider the difference that there is fundamentally different physical properties and behaviors in the recharge event. In the rejuvenation, it is more of a subtle change in the physical properties, and that may drive things. But then if you say 50 degrees in the silicic rejuvenation, that may actually have fundamental changes in the physical properties, especially if you're near the eutectic, right? And if you compare that to something that is mafic, you have maybe 100 degrees variation in temperature, where that is may have much less of an effect on the physical properties. So more of a comment, maybe.
Yeah. Thanks, Phil. I mean, it's a good comment, and part of this comes down to what I said. We're basically taking something that's a continuum and trying to divide it in two, which is a common issue in geology. And we all know controversies where people have argued about two ends of the continuum, where something in the middle is probably well, the answer lies somewhere in the middle. I mean, I think the reason we separate those is you can recognize those differences petrologically. So why not preserve them? But also that there is the capacity for some significant differences in the physical processes which result in initiation. On one hand, you're adding something very similar, and as you pointed out, perhaps that small temperature difference does still make a difference. On the other hand, you have that whole sort of volatile exchange that happens when you add a mafic magma to something more silicic. The classic Huppert and Sparks experiments. Your own papers on overturn. So our attitude is, at least let's track that. And then I think, another thing we really need is a greater understanding of how the petrological signals we see relate to the physical processes that are occurring in a magma reservoir that actually, and the chemical processes that then initiate an eruption.
Thanks.
And then I see Bradley has a question. So, yeah, go ahead.
Obviously, I love when there's incorporation of statistics, so I'm excited to take a look at that preprint. I like the 2x2 comparison. Makes sense to me, but I have a question and then a follow-up comment after you answer my question. So with the 4x2 or something like that, the p-value that you get, is that the probability that any pair of those in that comparison have a difference in distribution that cannot be explained by randomness? So in other words, you could have 3 of the 4 that have equal distributions and 1 that doesn't, and that would give a really low p-value?
Yeah, as I understand it, that's correct, Brad. So it basically just says that distribution that you see, the probability of that being correct if the null hypothesis is correct. So if there are 3 categories that are very similar and one that is quite different, that still would have a low p-value, right? Because the chance of that being chance of that happening, if the null hypothesis is correct, is still quite low.
Right. So yeah, so I think that in that case, because you have this compositional effect, right? And you commented on that, the idea that a felsic rejuvenation implies that it's a felsic mush that it gets put into. It seems to me that because of that compositional effect and the fact that you're not really comparing apples or you're kind of comparing the apples and oranges kind of thing, it seems to me that a direct comparison, the 2x2, is a more effective way of really teasing this out, because if you have just this one felsic system and 3 possible mafic systems, then that's going to override that signal.
Yeah.
So
I think that's a good point, which is why we use both approaches, and also that the 2x2 is much more accessible computationally, and the 4x2 is actually, the results I showed you are an approximation based on a sort of a Monte Carlo approach. So I take your point, and I will also say that this is sort of early days in this statistical comparison, and maybe there are some people here who can think of additional ways to do that. The other thing we really need is what Christy pointed out, is more statistical power, either to break down into smaller categories to keep doing testing with smaller categories, or to be able to apply other statistical tests. For instance, the normal test you might apply in this case would be chi-squared, but if you have any category with less than about 5 to 10 entries in it, then the chi-squared only becomes sort of an approximation. Hey, Sumit, I actually have a meeting now, so I might have to let Christy answer the remaining questions and peel off.
Well, thank you very much, Adam,
Thank you, everyone.
being here. So yeah, I'm looking to see, are there other questions? I had something. So I have a question here on chat saying, so I have a particular question. So what can drive a volcano to extinct? Okay, so yeah, well, whoever wants to keep that on.
I mean, that's an excellent question that I don't think that the work we did really is able to tackle, which is what essentially, reduces these particular initiation mechanisms that we're talking about. And in that cartoon that we showed at the end about sort of the different trends in the different characteristics of the different initiation mechanisms, we put some questions down at the bottom, like, what is the difference? Why do you see these different initiation mechanisms at different systems? Does it have to do with, for example, magma flux from the mantle? So, do we see the felsic rejuvenation in systems where we have a higher magma flux in contrast to systems where we see mafic recharge, or other questions like this? So I think future work will help us start to really dig into what produces different initiation mechanisms at different volcanoes, and start to, maybe work towards a larger question of, well, why do we have particular initiation mechanisms, and then why do they stop?
Well, that gets me to a related question I was going to ask Chiara about, actually. So in the Stromboli example, when you see that the marsh is disrupted in some cases and not, is that correlated to the volume of the eruption somehow or not?
We haven't really looked at in particular to the volume of eruption, but the volume of eruption usually is quite similar and low at Stromboli. Even when we talk about the paroxysm, they have really low volume. I think it's more related to somehow the frequency and the volume of recharge that we, well, clearly it's quite difficult to calculate the volume of recharge, but we can see that the frequency that we have of the recharge can somehow be related to the disruption of the marsh. So during the 2003-2017, there has been quite a lot of recharge that we see, and what we think is that at some point, really the marsh was kind of obstructing the system, and by the time you get more mafic recharge, at some point it's just starting to recreate a magma pathway, and then allow to have more recharge, or allow the recharge to have a more high frequency, kind of moving a little bit more free. So what I have presented is the work that actually I'm doing on the 2019 paroxysm. So in July and August 2019, there have been two major explosions at Stromboli with very close spaces, which is very unusual for paroxysm at Stromboli. Usually you have paroxysm every few years. In this case, they were in less than 1 month. And actually, what I see is that somehow the marsh has been already destroyed between 2003 and 2017. And we really have evidence that is going back to the same, with mafic recharge really recorded by the rim of the crystal, that we don't have during 2003 and 2017. So I guess it's more really due to how the marsh is kind of obstructing the conduit.
I see. And does the residence time drop in the second paroxysm?
For 2019?
Yeah.
Actually, no, they are pretty much the same. I mean, they are very short time scale for both paroxysms, which is very interesting.
Mm-hmm. So looking to see if somebody, there's a question from Jamshid. Go ahead.
Thank you. Yes. Hi, Dr. Till. Thank you for the great talk. I was just wondering if I had a question about maybe some getting some potential advice for a system that there is a fresh juvenile basalt kind of intruding into a system that has both old basalt which is similar in composition, and then an older, more crystalline trachyte. Just if we're, I like the idea of making a common nomenclature between recharge and rejuvenation. And I feel like personally, up until now, I've been using them interchangeably. So I was wondering how you might treat this situation where it seems like you're having both recharge and rejuvenation, and any advice for a student?
That's a great question. I mean, I think if you step back a second, one of the impetus to define a difference between mafic recharge, where we have a large contrast in composition between the intruding magma and the host magma, versus rejuvenation, where we don't, is that the physical process of what's driving the eruption might be different in those two cases. So you can imagine in where we have a very similar composition of magma intruding a reservoir, that maybe we reach that critical overpressure by essentially just a volume problem. Like the crust can't accommodate the volume of material that's trying to be stuffed into it. And that reaches the overpressure to drive tensile failure and crack propagation and eruption. Whereas in recharge, it's one likely possibility is that it is the sort of meeting of a volatile rich mafic magma with a more crystalline or evolved silicic chamber, and that then we have volatile exsolution driving the volume increase to reach the critical overpressure to drive the eruption. And so if it were me, I'd be asking the questions about, in this system, what seems to be sort of maybe like the dominant process that is underpinning the eruption. Is there a significant volatile cargo that, you know, could be part of the story in this case, or is it more likely a volume problem? But we lay out some more specific criteria to try to put these things in bins rather than on a continuum in the preprint. So I also invite you to download that, and hopefully there'll be a peer-reviewed publication shortly to follow. It's in review right now.
Great, thank you so much.
So I also have a question on chat again for Chiara again. So Chiara told us that she likes pyroxenes to determine timescales. Any reason for not liking other phases? This is from Francois Holtz.
No, actually, I do also like quite a lot plagioclase. Is that, well, pyroxene are definitely simpler than plagioclase, so you don't have to account for the low amplitude oscillation. And then somehow I started to work on pyroxene that they really track the crystal system, particularly for a system like basaltic system like Stromboli, or a more intermediate system like Popocatépetl and Colima, and they really track all the history, the crystallization history, and seems like they can give quite a lot of the answer. Instead, the plagioclase can come later or has more complication. So no, probably just got trapped in the pyroxene loop. I'm trying to escape. I'm trying to work on other phases, but at the moment I'm still trapped in the loop.
Good place to be trapped in.
Yeah. Sounds familiar, like somehow.
Other questions? If people are waiting for it, I have a question for both of you, and actually everybody else out here as well. So what you've been hearing is that, you know, temperature plays a very critical role in all of this, and particularly if you're looking at recharge, where we have maybe a crystal cargo from something previous, and the surrounding melt is different. How well do you think we can determine the temperatures? And it boils down to using some thermometer and something coexisting with something. And so what are the risks or uncertainties, or your thoughts on that, you know, whatever, temperatures in these complex systems? Whoever wants to go at it.
Well, that's, I guess I would just kick on, since I talked about temperature quite a lot. Yeah, I mean, that's a very difficult question. I mean, trying to get the right temperature and trying to reduce the error on the temperature is really a tricky task. So we have used a combination of different things. For example, in system where like the mineral liquids thermometer, but also coexistence of phase, particularly the 2-pyroxene, and trying to see if they match. In other case, well, the ideal thing to reduce really the error would be trying to kind of calibrate the thermometer for the system. At Stromboli, with Silvio Mollo, we were able to calibrate a specific thermometer only for the present-day activity of Stromboli, so for the shoshonitic basalt of Stromboli, very specific one, and the error on the temperature has been a CPX liquid thermometer, and the error has been reduced to 6 degrees, but you can only use for that system. So it's always trying to use multiple system and thermometer and see where you get, I suppose.
It's use different things to converge and things. So, Chris, you have thoughts on that?
I think it's a really important question as we continue to do more and more diffusion chronometry and try to put our results in context. Dr. Chiara Brugman, who did her PhD with me and is now a postdoc at Carnegie, and I have a forthcoming paper in Contributions to Mineralogy and Petrology, where we look at the relative size of the uncertainty from temperature versus all of the other parameters that go into diffusion modeling through Monte Carlo simulations. And that's a nice illustration of the fact that, you know, temperature isn't a relatively large uncertainty. But there's other, like our analytical uncertainty and other things. We really, when we need to incorporate those, of course, and then when we put them all together, that the relative uncertainty from temperature is only like one part of the picture. So I think that when we include all of these things, this is why, for example, in our study, Adam and I chose to bin things categorically, because I think as we do more modeling and use these kinds of approaches, we see that there isn't only one best fit essentially to the diffusion equation in these situations, depending on our model parameters, or other ones provide a very similarly low misfit. And so this question then becomes, how do we, what values are we certain in our volcanic system and putting them? So I feel myself that I tend not to now report timescales for the final interpretations that people might take and put in another study, except in terms of order of magnitude. I can put a number with a 2 sigma on it in my study, but the chance that that was isothermal diffusion, as Chiara nicely has shown, is pretty small in most cases, right? And so we want to make sure that we're always putting that assessment of uncertainty and the relative proportion of that uncertainty from temperature in our studies, I think. So I'm sure most people here would agree with me. So
yeah, I mean, yeah, those are very good points, both of you. I'm just wondering if we end up pairing, a crystal with a liquid or something. I mean, you'll always get a number out of it, a temperature, but if, that liquid never saw that crystal, then that number is not very meaningful. I mean, if there are ways of telling that, and Chiara was pointing out, if you use different systems, that kind of filters it out a little bit. Because if you're getting some random number, it won't get the same random number by multiple methods. But yeah, it's just something that I've been wondering about, and I thought I'd ask everybody to hear opinions on that. So there are other questions or comments, final ones. Seems like everybody's very happy. So getting a lot of messages saying thank you to all of you for the talks, and people seem to have enjoyed it. So I can join in thanking the two of you and Adam, who's not here right now, for doing this. And I think this gives us a lot of food for thought, and we can go back and use a lot of this in our works. So I'll just let people know that we'll have another one of these sessions in a month. And now for those of you from the US, that's actually exactly on Thanksgiving Day, unfortunately. So maybe, before your turkey, you want to get some good diffusion talks in. So Maren Kahl and Elias Bloch will be talking in about a month from now, and we'll send out the announcements and everything. So thank you all for joining us, the speakers, and all of you for coming in here, and have a good evening, morning, day, whatever's ahead of you right now. Okay, bye-bye.
Thank you very much. Bye.
Bye-bye.